Welcome to Week 4 of Introduction to GIS. This week we are talking about projections. In order to really understand projections, we need to talk a little about Earth measurement and coordinate systems. You can't squash an orange peel flat without breaking it into many pieces. Believe me, try it sometime. If you manage to keep the orange peel in one piece and then squish it down, something is going to give and something is going to distort. In the same way, we can't transfer the spherical surface of the Earth onto a flat surface without some type of distortion. The methods used to transfer coordinates from the sphere onto a flat map are known as projections. To ensure that the Earth's size and shape is studied accurately, geodesy, a branch of science responsible for measuring Earth's size and shape with surveys and mathematical calculations, is used. Before we project the actual Earth onto a surface, we usually simplify it. While the Earth appears round from space, when measured, it is actually flattened at the poles and bulging at the equator, meaning the Earth is not a perfect sphere, but actually a slightly oblate spheroid. An ellipsoid shows a smooth, simplistic representation of the Earth. A particular ellipsoid with particular values for equatorial and polar diameters is often used in projecting and measuring the Earth, particularly for highly accurate measurements such as surveying. Looking at this diagram, we can see an ellipsoid surface, a geoid surface, and a topographic surface. The topographic surface represents the actual Earth. The geoid surface represents an approximation of the Earth, and the ellipsoid surface is what we use to represent the flattened Earth. You can see how these vary slightly. A dozen ellipsoids are in common use around the world. Each ellipsoid flattens the Earth in a different way and is chosen based on the part of the Earth you are mapping. Here's a table showing some of the most common ellipsoids. The Clark 1866, the Geodetic Reference System 1980, and the WGS 84 are some of the most common ellipsoids that you'll see in GIS. The Clark 1866 is often used for North America, while the WGS 84, or the World Geodetic System, is used by NASA, and this is often used to depict the entire world. An ellipsoid can be used to measure distances on the Earth's surface without having to account for things like elevation changes, gravitational pull, and landforms. To account for the reality of the Earth's surface, geodesists use a geoid. If we look at this top diagram, we can see the ellipsoid surface is smooth. The geoid surface accounts for some but not all of the topographic changes. The geoid is a shape that is constructed using the global mean sea level and as a result takes a location changes into account. Since gravity and the Earth's surface are irregular, the geoid is not a smooth surface, it cannot be represented with equations easily, so it's rarely used for mapping. Datums are often based on geoids and are generally chosen based on the location you are mapping. Depending on which location you're mapping, you would choose a different datum. There are two main types of datums: a horizontal datum, which is a collection of points on the Earth that have been identified according to their exact location, which is something like their latitude and longitude, and a vertical datum, which is a collection of spatially distributed points on the Earth with known heights, either above or below sea level. As you can see here, there are a variety of different datums to use depending on which area of the Earth you are looking at.